Thanks, Michael, and good afternoon, everybody. And thanks to CRC for this opportunity to be here today. It's a great pleasure. What I'm going to talk about today is innovation in agriculture and trying to come up with new and innovative products to improve the productivity of hostile soils in dryland agriculture in some of our farming system. I hate to run out of time at the end of the presentation, so I thought I put right at front the important people who contributed to the program of research. So we've got 3 projects, 2 in program 3 and 1 in program 4. And the progress that we have made is due to hard work and intellectual input of many people. And the top row is the New South Wales DPI staff. Many of them are in this room. And we have collaborators from Murdoch University, Newcastle, and University of Southern Cross, and also we've got participants from industry and also from universities outside Soil CRC providing help and input with the project. So the problem, the impact of multiple soil constraints in Australian agriculture is well known, and I put here 3 major constraints that is affecting our economic performance of the water of the farming systems. Sodicity, which has an impact on soil structure, is one of the major limiting factors for productivity and profitability of the system, and there are estimates of $1.3 billion per annum loss in production, followed by acidity and salinity having similar impact. And the problem is that you may have a beautiful crop one day, which may worth over $20 million estimated for that season, and then a few days later, and this is not strange over the last 2 growing seasons, that crop worth nothing. And the reason for this is hidden in the soil. There are so many limiting factors in our soils, which I refer to multiple soil constraints, whether it is acidity or sodicity or salinity, compaction, and limitations in nutritional uptake of the crop, together result in a major deficit like this. For the rest of this presentation, I will focus on alkaline sodic dispersive soil. I just want to mention at the beginning that we have successfully developed products, innovative products for acidic situations, especially for subsoil acidity, but given we have only 10 minutes for today's, I think I will focus on sodic dispersive soil. So there are different issues that happens at the same time in some of these really difficult soils. On top left-hand side, you've got a Petri dish that illustrates the problem with the poorly structured behavior of these soils. You've got dispersion that happens due to that imbalanced cation on the clay, and then you've got a slaking on the left-hand side, which also related to that very low organic carbon content of our soil, especially in the subsoil. Together, you get a very poor structure of these soils, especially when they are hydrated, and when they are going through the wetting and drying cycle, you start seeing hard pans created in soil and in the subsoil that affect your water dynamics, nutrient uptake, and also a major important issue for your root penetration and water use. And what we are trying to achieve here, we are trying to improve the water use efficiency of the farming system. At the end of the day, any soil management has to target that economic performance of system water use efficiency, and that is the heart of our research in terms of developing products or re-engineering the soil that will address that issue. So for correction of alkaline sodic soil, at the moment, the industry has limited options. The farmer practice is usually gypsum application, surface application of gypsum, which will improve that extremely alkaline condition and also provide some sort of calcium. However, it has little impact on your subsoil, and even on the topsoil itself, there is a lot of hit and miss. We don't have consistent results. Over the past few years, there has been other approaches to improving the productivity of these soils. We looked at precision placement of gypsum. We looked at organic amendments on its own or in combination with some other minerals and nutrients. Again, we started to improve the productivity of the system, but its adoption and the future of some of this work still is not showing a lot of promising. And I'll give you an example. Some of the organic amendment application requires 20 tons per hectare of a product to be applied, yet alone for that to be incorporated into the subsoil, which is really difficult to be adopted, and you still don't have that proof of concept that it's going to work. So there are advances in material science, in chemical engineering, and I thought, how about we bring some of those latest advances to agriculture? The use of polymers, the use of nanotechnology that manipulate the particle of a product and enable the functionality of a very conventional product such as gypsum or lime to be improved, and try to target the subsoil by these recent advances in formulations of some of the product. So one of the possibilities, and today I'm going to talk about some of the product that we developed to improve soil structure in these poorly structured dispersive alkaline soils. Pyrogenic carbon, better known as biochar, which I will avoid to use that terminology today, has a very interesting morphology and capacity and characteristic to offer as a carrier for some of the product that we want to load. A raw biochar or a pyrogenic carbon is really simple itself, but we can actually manipulate that by adding metals or a mineral phase into this product. We can post-treat it with the chemical that we want to, and on the right-hand side, coming with a new product that for a specific problem that we want to tailor in that soil. What has been happening in the past couple of years, this is the result from the work that one of my colleague, Yuning Fang, has done. We found that in some of Australian soils, in most of Australian soils in dryland agriculture, when we introduce a mineral into the soil, and in this case, we are focusing on iron mineral, specifically short-range order mineral, with goethite being an example, we improve the carbon use efficiency of the system. And we thought, okay, what's going to happen if we include that mineral phase into our product? And although those differences are little on the right-hand side of this slide, you're talking about between 10 to 60% improvement on the carbon use efficiency. And remember, the lack of carbon and that very important type of carbon, which is the microbial biomass carbon, for the soil structure is massive. We can actually start to look at improvements of soil structure and aggregation significantly by having products that provide that into the soil. So how do we tackle some of these formulations? It starts with a good coffee, and I've got evidence that the quality of coffee consumed has a linear relationship with the effectiveness of the product. So with Lucas on the right-hand side of of the room, we spend a lot of time to discuss those formulation, and then we start small. We've got technical assistants that helping us in the lab to make some of those products, and then we characterize them. We need to understand what are the morphology and the chemistry of these products, and then with the team, we do a smaller scale proof of concept studies in the lab. And in this example, I'm going to focus on two products that we compared with the control, which you can call it the farmer practice, or agricultural gypsum, which is the industry common practice. So the third product there is a carbon-coated gypsum, and the right-hand side is also a carbon-coated mineral in dispersion, in sub-micron size dispersion formulation. So it's in a liquid form. And here in the lab, very quickly, as a quick assay, we showed how we can improve the tiller of the plants over a couple of weeks of experiment. From here, we go to glasshouse studies. First thing first, I just wanted to show the morphology of some of these products. What you see on top left-hand side is a biochar or a pyrogenic carbon loaded with the additives that we formulated in the lab. So the sub-micron sized image of this product, you see two phases. There is a phosphorus phase, and there is a mineral phase, and the mineral phase has iron in it, and it also has calcium and sulfate, which is important for the imbalance of the soil structure when dispersion is important, and the carbon itself is important for the slaking behavior of some of these soils. We also quickly look at the possibility of arresting the dispersion of the soil by this product, and you see from left to right-hand side that we actually have a good demonstration that how the dispersion of some of these highly alkaline dispersive soil can be arrested in response to adding low, medium, and high rate of these product application. As I mentioned, it's good to look at what happens in the soil, but we really need the productivity to be manipulated. So in the glasshouse, and my colleagues on the left-hand side become an expert in glasshouse experiment after 2 or 3 years, and probably they hate me about it. But we run experiment and we characterize different components of this, and I'm going to focus on what happens to the plant because that's really the assay that we want to look for, and I don't have enough time. So what you see here, on the left, a control treatment, and on the right, the amended treatment. In this case, this is our submicron dispersion formulation that dramatically increase the biomass and the grain yield. We see differences up to 60 to 70% in terms of how many grain yield affected by those treatments. And then the other important indications, greenness indicate tolerance. We do a simple measurements of the chloroplast content of the plant, and what we see is that when our control or agricultural gypsum treatment start to mature, we still have a very green plant in our amended soil. And this is extremely important because that means an improved photosynthesis, and photosynthesis is the key determination factor for your yield improvement. And here we can show that in this particular experiment with these 2 amendments, we actually improved the photosynthetic capacity of the plant by about 16%. So I just want to focus very quickly, and I don't have time, yes. Forget about the left-hand side, that is the synchrotron-based RN analysis. On the right-hand side, we demonstrated when we have a carbon-coated mineral in the system, we actually transform the speciations of RN. What it means, this process activates electron transfer in the soil and in the rhizosphere that has a very significant consequence on your ion uptake and the way that carbon will be stabilized in the soil. Now, if I have 1 more minute, please, and I know that Amanda will hate me about that, but what happens when we go into the field, and Meg actually should correct that 6 milestone. We have done a lot of field experiments, and we have the capacity with our industry partners to look at the efficacy of some of these products in the field. My colleague, Dr. Wilhelm, will talk about calcareosols and how some of our products transform the phosphorus nutrition in calcareosols in South Australia compared to typical practice or continuous phosphorus nutrition from other sources. We also have demonstration that how the crop performance in the field in southern New South Wales can be affected by some of these products, completely transform the productivity of the system, and now we are taking a number of these products and innovative strategies into the field within the program to look at, and already last week we see some differences on the right-hand side of how the plants look better in ameliorated soils. So one last comment. Last week, a very high impact paper was published after 3 decades. Scientists showed how the photosynthetic manipulation of the plant can increase the yield by 30%. GM approach to improve plant productivity, and I'm wondering sometimes the hidden opportunities in the soil, why we don't see the elephant in the room and looking for the mice. Because with that electroactive rhizosphere, which I don't have time to approach to talk about it today, there are significant opportunities to re-engineer that very hostile soil or subsoils by adding the innovative products and amendments to improve the productivity of the farming system in Australia. Thank you.